probably the ambulance is going to be coming right shortly if it's not already there. Hopefully it's not anywhere, not anybody that you know.
Yeah.
Kind of like my friend Vince across the street from me here. His wife is not doing well, and the other day they had 3 ambulances there. I guess they came from all over.
Jim?
Yes, sir.
On the Darwin site, you look under what they call the 1073 series, Darwin plane insulators. You'll see all kinds of the ceramic insulators, and you'll see some of the same insulators that I was talking about that are long and narrow, so I think that would probably work. They're not overly heavy.
Okay, I just sent you a link to the ones I was looking at. I think they may be maybe we're thinking the same thing, but take a look at the insulators I just sent you.
Okay.
What lengths are you looking for?
Looks like these things are about 7 inches long, made out of glass.
Roger.
You gotta have a power to pull those things up.
How many do you need, James?
I need 2. I just sent you a link to the ones I'm looking at, Ed.
Yeah, I've got a huge collection of antenna insulators here.
Well, as you probably heard, I want to stick with this antenna I have, which is a 40-meter, 80-meter antenna. I love it. The ends get real hot.
How long is it?
The antenna is just about 5 feet longer than a 40-meter dipole, so there's a lumped inductance at the end. Then just 5 feet after that is the end, and it gets very hot.
What's the voltage at the end? Do you know? Any idea what the voltage is?
No, I do not know that figure, Ed, but I know that when I was first flexing the muscles on my Henry 2K, I heard my antenna come down and clunk on the roof.
Oh, you must have had some sort of synthetic fabric on one end.
Yeah, so ever since then I got very apprehensive of running any power. I know the ends are getting hot, and I'm close to a tree, so I gotta get around that.
Jim, the 1070, model 1070, 7 inches long.
How many times can that hang up against something before it breaks?
What was that, Sandy?
I said, how many times do you think you could have that thing bang up against something before it falls apart and breaks?
I mean, that insulator, that's just...
Yeah, I'm not much on glass insulators for that reason, but that's why I asked.
These are ceramic.
Well, glass, ceramic.
Oh, there's a difference. I think ceramic is structurally much stronger. Can't remember what the force is when you pull things apart. Stress?
I sent it to you, Andy.
They handle a higher stress than glass does.
Okay. I'm probably using glass in a much wider context. It doesn't make any difference, Bill. I was just asking.
Oh, no, that's okay. It's a good question.
Yeah, glass would be my last choice. It's too finicky. And the older glass gets, the more finicky it gets.
I feel like it's brittle.
Yeah.
Like in the windows of my house.
Like the windows in my house.
My house is almost 100 years old.
Do you get sick to your stomach when you look out your window?
No, because the idea that glass never solidifies, that's not a true thing. Glass, when they were made, had the waves in them when the stuff was made.
Glass is a liquid.
So it doesn't shift with time, and yeah, but some of my windows are wavy because they weren't made by a very good company, I guess. Wavy glass. Anyway, this is an interesting discussion. On my 40-meter antenna, I've never had any of those insulators have any trouble at all. We just use those, those plastic dog bones. But I knew that the voltage at the end of the inverted L was going to be high, so I went with actually it's the alpha delta version of the Budwig, which has a few more fins. I think the Budwig's got like, 2 or 4 fins, and I think the alpha delta's got like 5. So the effective length is really long.
Yeah, that's a big antenna.
Well, is this heat generating function if it's being dual band?
It's due to, the voltage gets higher because it's got a coil in it, which increases the Q of the antenna, so that raises the voltage at the end.
Considerably.
Yeah, that's Kenny explained that to me. I didn't know that was something that happened, but it does.
Be fun to see exactly how much heat you could load into the end of that, at what the temperature would be at that point.
Well, I don't know so much temperature, it's just voltage. The only reason you think you'd get heat is if the thing started arcing.
I wonder if I could get a signal report, please. November 0 Foxtrot Uniform.
10-0 FU, W6AD, you're 5/9 east of San Diego.
Oh, okay. I'm in Philadelphia, so big. Thank you, Ken. Appreciate it.
Okay, well, it just means we've got short skip.
Very short.
You're barely hearing. Where's he at?
Down the hill from me in Chula Vista.
Oh, no wonder. Okay, you can't. Wow. At least I'm hearing him. It's little things that I could copy.
Anyway, that's what we're doing.
Frequency and tune this thing up. I'll come back to that.
Okay. Anyway, that's what we're doing, Ned. We're having fun discussing the voltage on loaded antennas and thus insulators to combat that problem that may or may not occur.
Yeah, I'm thinking if you had a piece of Dacron on the other end, it probably didn't like the heat. But glass and ceramic, I doubt if you could get it hot enough to. I mean, what let go? It was a piece of synthetic material.
And of course, the insulator could have broken when it hit the roof.
Well, that end of the antenna wasn't over the roof, but that end of the antenna is where it let go. And looking at what RF engineering has to offer, but they want an arm and a left, you know what, for one.
Well, the things you need to consider are cost, weight, effectiveness, longevity, I guess, and not necessarily that order.
Well, the RF pots right up the road from me. I sent you the link, Andy, just so you could have a good laugh.
Now that's an insulator, Jim.
Yeah. That's mil spec.
7680, it's half past.
Like to get a couple of those.
Well, you certainly wouldn't arc them. They're only $40 a piece. Let's see what Ed has. I've heard of Ed's famous insulator collection.
All right, Ed. I just sent you to a link to what I want.
He's probably got a couple of them there in his box. Geez, I gotta get changed and get up to the store pretty soon.
Cool.
Grocery day.
W1WI. Yeah, you know, it's too bad, Andy. I've got all this Delra in here. And I wonder if I could use that.
Well, I don't know why not. Insulating properties are good at that stuff, isn't it?
Yeah.
I don't know how the sun affects it. That'd be the only issue.
Well, stuff is impervious to sun.
Okay, and it's very strong.
Very strong.
So why couldn't you just cut off 7 or 8 inches and drill a hole on each end and you're good to go?
Yeah. I've got to find someone who can put it on a lathe and turn it. Put some ribs in it.
Well, that would increase the effective length. That's what the ribs do.
Oh yeah, I didn't think about that.
Yeah, that's why they like the Budwigs and the Alpha Deltas. That's what the ribs do. They just increase the effective length.
All right, how am I going to do that now? I don't know. I don't have a lathe. Might be cheaper to go out and buy a pair of those RF engineering jobbers. I can go up there and pick them up.
Or you call up HRO and get a couple of Budwigs.
I'm not sure those Budwigs are going to cut it, Andy.
Well, I'm pretty sure they will.
Tim, I just sent you a link on foil ductance versus where it's placed in an antenna that's built like yours that acts as a somewhat of a trap or an RF choke. It's kind of interesting. Well, anyway, give you something to look at.
All right. Just sent you off something to look at. This is what I'm looking at right now. Looking at yours.
There's a graph in there that shows required loading coil inductance as a function of coil placement.
Ah, goes to infinity, Andy. Yeah, goes right up to infinity. So, how does that work along with end voltage? The end.
Well, because you need more and more inductance, that means the more and more coil you add, the shorter the stub is beyond the coil, the higher the voltage.
Okay, I'm looking at this thing here. It looks like a calculator, antenna configurations using custom dimensions.
So that will answer your question. Can you alter the length and the number of turns? This speaks to that. Now, I haven't studied any of this, so it's just something that I discovered and thought that it might be informative for you.
Many years ago, Ray and I, CWQ, played with a 2-element 40-meter Yagi. It was a Mosley. It had coils in the middle. We didn't like that, so we started playing with the Dargon thing with coils farther away from the middle. We came to a spot, and I don't remember how far out it was from the center, where the antenna seemed to play a lot better than having them in the middle. So we did something similar with the 2-element Yagi.
Well, if there were an optimum distance, then you would think that there would be a function that you could determine what an optimum value or peak value is, like when you said a derivative, an inflection point, Jim, for maximum or minimum. So if you have a function that has a peak, but this isn't like that. This is like a tangible function.
Yeah, this doesn't have a maximum. This is an exponential animal.
Yeah.
And of course, you got to remember too, we're dealing with antennas here, and we're dealing with dipole antennas, or quarter wave, half a dipole. And so the farther out on the antenna you get, the more turns you're going to need until you're at infinity at the end of the antenna. But also, the less current you're going to be running through the coil.
Now, wait a minute here. That coil, that lumped inductance for this 80-40 configuration, that lumped inductance is placed precisely at the end of each side to be a quarter wave on each side of 40 meters. And that's the reason why that inductance is calculated. So you have a nice half wave on 40 meters. And that's the reason why you're stuck to that inductance and hoodwinked by that high voltage. There's no way to change it.
Of course there is. You can take turns off the coil, and it'll still, I don't know how many turns or whatever they design, but you could leave it at the end of the 40-meter antenna. You could take turns off, but unfortunately you're going to come to a spot, when you take enough turns off, you're going to start loading the coil too, instead of having it look like a big lumped inductance at the end of the 40-meter antenna. And I think that's what we've been talking about.
Yeah, so you cannot move that lumped inductance. It's got to stay where it is.
No, but you can change the inductance.
Yeah, but you won't have a nice 40-meter animal anymore.
Well, it depends on how much you change the inductance.
Yeah, but I like the idea of having a independent 40-meter antenna.
Well, exactly, and that's why they do it that way, Jim. That's what I'm getting at. If you want to have it resonate on 40, it's got to be at the end of the 40. Now the question is, how much inductance do you need before that coil disappears and just becomes like an insulator?
So if I stop messing around with the inductance of that coil, and for trade-off, let's say that coil stays where it is, and let's say it's got 50 henries. 50 microhenries of inductance, and it's placed right at the 33-foot length on each side. And I decide, okay, I've got 5 feet stub for 80-meter resonance on the other side. Let's say I want to take that coil and I want to cut the inductance in half and go ahead and somehow lengthen the 80-meter stub on the other side. How is that going to affect the voltage, and how is that going to affect the resonant frequency of my 40 meter antenna? That's the question.
Well, I can answer that easily. Without any calculations or anything at all. It's going to lower the voltage at the end because you'll have less coil. And it's going to make the antenna seem a lot longer, so it's no longer going to be resonant on 40.
Okay.
It's like Mr. High Power. He makes these shortened antennas.
Yeah.
That's exactly what he's doing.
So let me ask you a question. You take a coil, let's say 70 turns, and just place it at the either end of your 40-meter antenna, which is cut a normal 40-meter length, then it should work okay on 40 meters whether anything is attached to the end of the coil. Is that correct?
That's my understanding. The way this antenna I have now is, if I were to short out that coil, in other words, if I were to put an insulator, anyways, restate the question.
Correct.
I think I misled.
What that coil represents is a very, very, very high impedance at 40 meters, much lower impedance for 80 meters. So on 40 meters, because of the high impedance of it, you could change a few turns on that coil, not alter its impedance that much, and you could actually calculate it, and then turn around on the far end, add just a little bit more wire so that it resonates on 80. So there is a factor in there where there needs to be, there must be a point where there's an optimum inductance that gives you, well, depending on the inductance is how long that lead has to be beyond the inductance for 80 meters.
Right.
There has to be a point reached where there's an optimum inductance that that allows you the longest lead beyond that insulator, that inductor.
I know, Bill, I know exactly what you're saying, and I'm looking at the curve that you sent me right in front of me here. It has coil placement on the x-axis, and it has the inductance on the y-axis, and it shows a nice exponential curve. But a problem with that is this is a multi-band antenna, and you get 40 meters interplaying with this 80-meter animal. So I think that's where I'm confused.
Now, and it has to do, if you calculate the impedance of that coil, 40 meters versus 80 meters, you'll find that 80 meters, the impedance is about 1/2.
Yeah, but isn't that going to mess up my nice 40-meter half-square antenna?
Well, not necessarily. Depends what the impedance is on the end of your meter antenna, and there is an impedance there. Maybe 3,000, maybe 5,000 ohms. I don't know. That has all to do with how close to the ground and yada yada and all that other stuff. There is an impedance number for the end of your 40-meter antenna. Now, if you put something that is 5 times that impedance value beyond that point, then it becomes invisible to that end of that antenna that's only, let's say, 3,000 ohms. You put an impedance in there that's, let's say, 15,000 ohms. That has no impact on that 3,000 ohm. It doesn't shut it. Does that make sense?
So by placing the coil in line, not at the 33-foot magic point, they're telling me I could shorten up the 40-meter end of it and still have it work.
Oh, no. You would use the same... now, here again, Jim, I haven't done this in the field. You remember that antenna modeling program that I told you about?
Yeah.
That would be ideal to come to grips with some of these questions you're asking. In fact, I've started modeling some of it as we talk, and so I can't tell you because I don't know what the mathematics is on it. I know that the end of the antenna has an impedance figure, very high, 3,000, 4,000, some number. And if you put a higher impedance beyond that, connected beyond that, it will not shunt or load down that end impedance. So therefore, it still acts as an insulator because of its high impedance. It's like putting a 10,000 ohm resistor in parallel with a 1 ohm resistor. I'll never see that 10,000 ohm resistor.
Well, isn't that what's going on with what I'm doing?
Oh, that's I think what you're doing. Yeah, exactly. So what you want to do is you want to kind of, let's say, okay, how much can I reduce this inductance and lengthen the wire beyond it? By the way, allows a little broader spectrum or bandwidth. So the shorter that stub is, the narrower the bandwidth, longer that stub is, the wider the bandwidth.
And bottom line is you don't want to screw with it because obviously the designer of the antenna has already figured that all in, and you don't want to take off too many turns of that coil or it starts becoming modable on 40 meters and screws up your 40 meter performance.
Well, that's what I'm saying, Andy, is that you could use, I'm sure the designer used a modeling program, antenna modeling program, and he used the radiation efficiency determine what he thought was the optimum placing of that coil.
Well, the optimum placing of the coil is at the end of the 40 meter antenna. That's a given right there. You don't have any choice on that.
Oh, I'm talking about the inductance of it.
Well, the inductance is as much as you need so that when you're operating at 40, that coil becomes invisible. It just looks like an insulator. If you run less than that, and it ceases being an insulator, it starts being a coil, and then you start loading it, and then it screws up your 40 meter antenna. So there's got to be a point there where you got a fudge factor. You need so many turns so it still looks like an insulator, and enough turns that it resonates the antenna also on the other band. Does that make sense?
Okay, if I can reflect back to you, what you just said was the inductance is such that the impedance of it so high compared to the end of the 40 meter antenna, it looks like an open circuit.
Right. This looks like the 40 meter antenna ends right there.
Okay. Now, what I'm saying is, you can have more inductance than that, and it won't impact your 40 meter antenna.
That's correct, and you should be able to even take that wire off the end of it, and it still won't change anything either.
Now, the question is, what is the value of inductance that you have to have so that it does not impact the efficiency of your 40 meter antenna?
I guess you could put the coil on an inductance meter and find out.
Well, I don't know how you do that because all that's going to do is tell you the inductance. But what is that inductance? What is that impedance that has to be at the end of the 40 meter antenna? Rule of thumb is that if your impedance that you're shunting something with is 5 times or more than the impedance you're shunting, then you can kind of practice for all practical purposes ignore it.
Okay, you're interested in specifics, and I'm just interested in how it works.
No, what I'm trying to do is just try to help Jim understand why it's that way. I don't know whether that's or not.
I just sent you a link, Bill. I sent the same one to Andy, and this is a picture of what I want to put up. And this is what I'm going to strive for. And I am going to have to stick with this and come up with better insulators, because I cannot change the windings on that coil at the end, because that's going to affect the 40-meter aspects of the antenna. If I were to put more windings on that coil, I'd have to move it closer to the end, but that's going to screw up the 40-meter end. It's going to change the resonant 40-meter aspects of the antenna. So the inductance of those coils are fixed in position along the length of the elements, the 40-80-meter elements. That coil is placed there at a magic spot. That makes sense, Bill?
The magic spot is the end of your 40-meter antenna.
That's the magic spot. That's where it offers a very high impedance. So it acts like a short right there. Acts like an open, rather. Acts like an open.
Okay, like an open. Now, when you go to a lower frequency, it has less impedance, so more energy gets through it. Is that correct?
At a lower frequency, that means that it's going to be looking for a higher inductance to be resonant. So yeah, it's going to penetrate into that coil somewhat.
When you get down to 80 meters, enough energy gets through that coil, and that along with the stub that you have beyond it looks very much like an antenna, which is a distributed inductance throughout its length.
Well, I'm looking at this article by Kilo Golf 0ZZ, and he's pretty much says it. I don't know. If you saw what I
got
sent.
that in front of me, and it's not a whole lot different than the one that you currently have up. Is that right?
That's what I have up now, yeah.
Okay. Now, does the antenna that you have up right now have that same exact tail length?
Roughly, yeah.
Okay.
And it gets very hot at the end.
Now, that's because of the high voltage. It's almost like a bandograph machine.
Yeah, did you see the link I sent you of the insulators I'm interested in using on the end by RF Parts?
No, I'm going to look at those now.
But did you get it?
Oh, I got the one that showed the insulators, the white ceramic insulators, the several of them.
These are what I want to get. I'll send this out to you. I think this is going to solve my problem. All right. On the way. I'm going to get me a pair of these from RF Parts.
Yeah, okay. I think those, that looks, how long is that? Let me look at it. 7.5 inches long. That'll work. I think the ones that we used when I was in the military were 6 inches long, and we ran 3 kW.
Okay. Oh, looks like I'm going to have to go that route.
Site that I sent you, it shows the coil placement versus the inductance required. Shows it goes up to infinity.
Right.
Wish you had the equations to go along and tell what that curve really is.